Hello everyone, I want to welcome you back to this lecture series. Once again, Emeka Udenze is on the microphone. In today's lecture, we're going to be talking about atomic weight. Let us take it off from there. We have a few learning objectives that we want to that will help us understand the scope of this lecture today. Number one, we want to be able to describe what is the relative atomic mass of an element, what I call RAM, relative atomic mass of an element. Two, we'll be able to describe the molecular or formula weight of compounds. We'll see how this is done. Finally, we're able to calculate the molecular formula weight of compounds using atomic weight of constituent element. These are the things we're going to aim to achieve at the end of this lecture. So let's take it off from there. So let's start with the relative atomic mass. You see, when you look at your periodic table, you're going to see some numbers that are written below it, below the symbol and the name of each element in the periodic table. So take a look at what I have here. If you look at the periodic table, this is like what you have in the box of magnesium. Here you have, of course, the atomic number of magnesium 12. You have the symbol here. Now you have the name magnesium here, and finally you have this number. This number is what we refer to as the relative atomic mass, because this number provides a simple means of comparing the masses of atoms, and it represents the average masses of all the isotopes that exist in this atom. This atom exists as isotopes. So usually what we do is that we get all these isotopes and calculate the average. A good example would be if you're buying your beans. Most times when you go to buy your beans, right, you want to calculate the average of these. It's difficult to begin to say, okay, you want to weigh each of them one by one. But if you say, okay, one of them, if you assume that all of them weigh like close to the same average, what do? Is to take all of them and divide it to find the average. So in this case, most elements occur in mixtures of isotopes. And for us to have a better understanding of them will be to take the masses of all the existing ones and find the average of them. So that is what we usually do. And this number is called the relative atomic mass. And like I said earlier, because it's an average, most times you see it written with a decimal place, with a fraction. Yes, because it's an average of different isotopes. So if you have, let's say, an element has different isotopes, and you want to calculate the average mass of that isotope, the average. So if it exists as A plus B plus C, you add all the three together and divide it by the total number, which is 3 times by 3. In this case, we don't use 3. We use the frequency of the occurrence of this element. We count that in percentage, which we call the relative abundance, as I'm going to show you as we move on. All right? So that is what we call the relative atomic mass. Now, this is different from the isotopic mass that we talked about in the previous lecture, right? Those masses we talked about, isotopic mass, were all in whole numbers. None of them were written with decimal places. So the atomic mass unit is actually measures that atomic weight, the atomic mass of each element. So it is either measured in atomic mass, the unit is either U or AMU. If you don't want to call it AMU, you call it U. All of them are the same. So they are used to express the average relative atomic mass of atoms. And the standard that was drawn is from one of the purest isotopes in nature, carbon-12. So with the experiment that was done to determine this, one atomic unit is equal to 1/12 of the mass of one carbon atom. So this carbon isotope is the one we are responsible. Of course, this is the carbon. This means carbon. Remember, we talked about earlier. This 12 here means the atomic mass is 12. So this is carbon-12. So carbon-12 has 6 protons and 6 neutrons. And when you add those together, of course, 6 plus 6, that gives you atomic mass of 12. So one carbon-12 atom has a relative mass unit of this. So what it simply means is that one carbon-12 weighs exactly 12 units. So an atom that has twice of that mass, an atom that weighs twice the mass of carbon-12 will have an atomic unit of 24. So the atom with the mass of equal of 1/12 of mass of carbon-12 will weigh the mass of 1 unit. So carbon still is the arbitrary element chosen and used to calculate the various atomic weight, atomic masses of all the elements in the periodic table. So the atomic weight is just the relative mass of the average of all the elements expressed in that atomic mass unit. So if you have your periodic table very close, I want you to look at it. Take a look at your periodic table now. So the AMU, or the atomic mass unit, is the what? Is the unit of atomic mass. So the atomic mass itself is measured, the atomic mass is actually measured in AMU or U. So let's see an example. If you look at the periodic table, chlorine has atomic weight of 35.45. If you look at this, chlorine is number 17 in the periodic table, and it has a mass of 35.45 U or AMU. Oxygen, on the other hand, has a mass of what? 16. Look at it here. It's written, look at it down here. 16 U or AMU. Whereas phosphorus, on the other hand, has what? 30.97 U or AMU. So these numbers, you're not expected to memorize them, because most of your exams, you're going to actually have the periodic table by your side to look up the numbers of the individual, the atomic weight of this individual element. And of course, like I said, in the periodic table, the units are not put there, but you know that these units, the units as you see them there, are actually measured in atomic mass unit, U or AMU. So let's now begin to talk about the different isotopes and atomic weight. So atomic weight of elements, of course, like we said earlier, is the average of the mass of the atoms present in that isotopic mixture. Of course, an example of an element is assumed to contain 100 atoms, 100 parts, which we usually say 100%. In fact, this number is actually what we call the relative abundance. Relative abundance in this case measures the frequency of the occurrence of each individual isotopes. So the relative abundance, which is measured in percentage of each isotope, represents the number of atoms that exist of each isotopes. So the total N, like if you're doing your statistics, the total N, the total number of outcomes, is usually equal to what? The sum of each of those masses contributed by each isotopes. In this case, you add the two relative abundances together in percentage to give you equal to 100 outcomes. And then you multiply the mass of each of them with the mass of each of them with what? The relative abundance. So what are we saying here? So in this case, I don't like writing a formula here, right? But I usually give a student this. So what you're going to do is that if you want to calculate the average atomic mass, so the relative abundance, assuming you have two isotopes, let's say isotopes A, an atom has an isotope A and B. So what you're simply going to do is to calculate the average is that you multiply the relative abundance of A times the mass of A. So if the mass of A, let's call capital M, mass of A, plus you multiply the relative abundance of B times the mass of B. And then you divide it by 100. Remember, the 100 here means you are adding, 100 here means the relative abundance of A plus the relative abundance of B. Because it's percentage. The total percentage of anything is equal to 100. So we're going to see example in the next two slides. So let's do the first one. It says determine the average atomic mass of boron that consists of 19.78% of boron. I told you boron 10. I told you it is usually given a percentage. With the mass of this is the mass of the boron 10 has a mass of 10.01 U and exists 19.78% of the times. Whereas boron 11 here exists 80.22% of the times with a mass of 11.01. So now, let us do the math. Let us try to calculate the average mass of this. Now, again, like I said, I don't want to give a formula to this, right? I don't want to give a formula to this, but it is much more easier to take it to be that this is an average over 100, right? You multiply those masses like I put here. You multiply each relative abundance by the mass of the first one and do it for the second one and divide it by 100. Let's see what happens here. So here, get to the average atomic mass here now becomes equal to, I start with the first one. The relative abundance of the first one, 19.78 multiplied by the mass. What's the mass? The mass is this. So boron 10 has a mass of 10.01 U. Plus, remember this is U. I want to make sure that my U comes out really well. Plus, the second one is 80.22%. Of course, again, times, you're multiplying it times. This is boron 11, which weighs this, 11.01. Then you divide it by 100. Now, where do you get this 100? Some of you might ask. 100 simply means you're adding, okay, let me do it this way. Let me first. So add the total percent. Let's see, 19.78 plus 80.22. When you add this together, it's going to give you 100%. And when you divide it by this and do your math very well, you're going to get about 10.81 U as the average atomic weight or average atomic mass of boron. Let's compare it with, there's a mistake here. This, I'm supposed to change this. I just saw that. Let's compare with the mass of boron. So the true mass of boron will be, this is what you have in the periodic table. I made a mistake with the next one. So you're going to have 5 B, and then it has boron here, and then this is 10.81. This is what you have there. So if you look at this value, that gives you exactly here. So that means that this is the live correct data that was collected when determining or measuring the actual mass of boron, 2 boron isotopes, boron 11 and boron 10. So if you look at your periodic table, I found out that this particular calculation is legit, and it gives you the exact mass of boron from the periodic table. Now, you can always pause this video, try out the next one that we're going to do, check your answer and come back. Let us do the last one at this point. In this second problem, which will be our last, not our last particular, but our last in this problem, in this calculating average atomic mass, we're going to do exactly the same thing. It says calculate the average atomic mass, again, of chlorine, given that the natural occurring isotope consists chlorine 35 occurs 75.53% of the times and has a mass of this. That's what we're going to watch out. And then chlorine 37 occurs number of 24.47% of the times and has a mass of this. So what's the average atomic mass? So the average atomic mass, I'm going to call it AM here, will be, I start with the first one, multiply the relative abundance. Remember, this is the relative abundance. That's what they call it in percentage. 7.53 times the mass. What is the mass? This is the mass of that guy. 34.97 plus the other one occurs how many times? 24.47 times. And I'm putting this bracket so that you do the multiplication before you add them together. That's why I'm doing that exactly, so that your calculations will be right. Of course, this is U. Always put your unit U. And then you divide. Remember now, you're going to add these numbers together. 75.53 plus 24.47. If you add them together, it's going to give you about 100%. And when you do your math correctly, this will come out to be 34.45 U. And when you compare this to what you have in the periodic table, you see I switched both of them. In your periodic table, you're going to have, I switched both of these. And I didn't actually look at that until I started recording this video. So when you do that math for yourself, or when you look at the periodic table, you're going to have this. This is what you're going to have. So 17 on top, which is the atomic number, you're going to have chlorine. You're going to have chlorine. And then finally, you're going to have 35.45. So this is not chlorine. Just strike that out. So this is what you're going to have. So our number agrees with what we have in the periodic table, showing that we're actually very correct in our calculation. And that takes us to the next slide. Let's now talk about the relative molecular or formula mass. So the relative mass of a molecule, or what we call the formula unit, is expressed in atomic mass unit. Of course, in this case, we talked about individual elements, but you know that a molecule or a formula unit is made with what? More than one element. Example, if you have CO2, this is carbon dioxide, or if you have sodium chloride. Sodium chloride is the formula unit because it's an ionic compound. It's made up of sodium and chlorine. So if we want to calculate the relative molecular or relative formula mass for these two, what are we going to do? We're going to add together the atomic weight or relative atomic masses of all the atoms in the molecule or formula unit. So example, what is the molecular weight of CO2? Let's calculate it. To calculate the molecular weight of CO2, right? What we're simply going to do, now, it's important to clarify before I do that, is that molecular mass is used for molecules, covalent compounds. So let me write that down. Molecular mass is used for molecules. Let me write that well. Molecules, or if we call them covalent compound. Whereas the formula mass is used for ionic compound. What do we mean by this? Ionic compounds are compounds that have at least a metal inside them. Example, sodium chloride, one that has a metal. Yes, used for ionic compounds. So those are, and we're going to explain this by the time we begin to get into chemical bonding in a short while. So if I want to calculate CO2 now, what I'm going to do is to add the total number, add the sum of all the elements making this guy up. So what are we going to do? The first thing we're going to do here is that carbon, if you look at carbon here, let's go to carbon. Carbon weighs 12.01. So I'm going to say there's one carbon here, 12.01, plus there is two oxygen atoms here, but each of them weighs what? 16.00. So what I'm going to do is to say 2 times 16, oh, that one looks somehow, 16.00. 2 times 16.0 will give you 32. 32 plus 12.01 will give you 44.01 unit. So 44.01 corresponds to the molecular mass of carbon dioxide. So you should be able to know how to do this, and this is what we're going to be doing in a few problems. All right, let's finish up with a few problems here. Let's just finish up with a few problems on how to calculate the molecular weight. So it says, what is the molecular weight for the following compound? And first of all, the ones I give you are all molecular compound. There's no metal here. These are all metal, non-metal. These are all non-metal, non-metals, non-metals, non-metals. So these are all molecular compound. Let's do them one by one. So first of all, I want you to have your periodic table by your side and begin to look up the atomic weight of the individual element. Sulfur weighs 32.06. You add that plus. There are 3 atoms of hydrogen here, and each atom weighs 16.00. So what it means is that you need to multiply this by 16.00. And when you do that, this gives you, if you add everything together, gives you 80.06 U. For the second one here, we'll continue. Here there's carbon, there's hydrogen, there's nitrogen, there's oxygen. There are 4 of them. So let's start. Carbon weighs 12.01. If you look it up in your periodic table, plus hydrogen, there are 4 atoms there, so it will be 4 times 101. Hydrogen weighs 1.01 U, plus nitrogen, there are 2 of them there, so it's 2 times 14.01, which is weight of 1. Each nitrogen atom weighs 14.01 U, plus oxygen, there's only 1 of it, 16.00. And when you add everything up, this will give you about 60.07 U. I've told you in this lecture, try to restrict your calculations to 2 decimal places for convenience. And the last one we're going to do there is phosphoric acid. We're going to again add it together. Here hydrogen is 3. Hydrogen weighs 1.01, plus phosphorus weighs 30.97. There's only 1 atom, plus oxygen here weighs 16. 4 times 16.00. And when you add everything together, this will give you about 98.8 0.00 atomic mass unit. See, this is how you calculate the molecular weight of the following compound. Then the last one we're going to do here is that just to calculate the molecular weight, we want to calculate the formula weight. Again, this time we cannot say molecular because they're not molecular compounds. We just say formula weight or formula mass of the following, because look at this is a metal, this is a metal. So all these three are ionic compounds. So let's start. Here, calcium weighs 40.00. If you look at your periodic table, again, look at the periodic table here. That's calcium, 40.00. So I'm going to say there are 3 atoms. I'm going to say 3 times 40.00 plus 4.08 rather. That's 0.08 if you look at that very well. Plus these two affect everything in the bracket. So initially there's 1 here. So you multiply 2 times 1 is going to give you 2. So there's 2 phosphorus there. So it'll be 2 times 30.97 plus there was 4 already here. So 2 times 4 will give you 8 times 16.00. So this will be 3. If you add everything together, it's going to give 310.18. That is how you do that problem. That compound is actually calcium phosphate. For the next one, here we have sodium nitrite. Here, sodium. There are 3 sodiums here. So it will be 3 times 22. Each sodium weighs 22.99 plus nitrogen. Nitrogen weighs, there's one of them, 14.01. If you add everything together, you're going to get about 82.98 atomic mass unit. And finally, for aluminum nitrate there, aluminum here weighs, if you look at aluminum there weighs, aluminum is in group 3 and weighs about 26.98. So here, let's add it, there's only 1. So it's going to be 26.98 plus, now look at this bracket, affects everything inside. Nitrogen has 1 originally here. So 3 times 1 is 3. So there's 3 nitrogens plus, then oxygen is 3 here. But with these 3 outside, 3 times 3 will be 9. It will be 9 times 16.00. And when you add everything together, you're going to get about 203.01 atomic mass units. So these are the formula weights of the 3 compounds here. Now, we use the word formula weight because this compound has formula unit. And formula unit only represents ionic compounds that have metals written first in the formulas of the compound. All right. And having said that, we have actually come to the end of this lecture. Thank you for listening. Bye.